Precalculus, Chapter 3, Section 4, Exponential and Log Equations. So let's start by solving exponential equations by solving each side as a power of the same base. Sometimes you'll be able to do this with an exponential, but not always. So if you have one exponential of a base equaling another exponential of that same base, then you can set those powers equal to each other. So we have the powers m and n, and see how the bases are the same? So that means that we can set those powers equal to each other and solve. So when you're solving an exponential equation where this is the case, you want to rewrite the equation in the form of, meaning that your bases are the same, if you can. Then you can set the powers equal to each other and solve. So let's look at these two examples. So we have 5 to the 3x minus 6 equals 125. Well, I notice that I can rewrite 125 as 5 raised to the third power. So I'm going to leave the left side as it is, base 5, and the right side will rewrite it as base 5. Now my bases are the same, so I can set those powers equal to each other. It was like the m and the n in the general form. Then you're just going to solve for that simple equation, and you will get x equals 3. All right, look at example B. So we have 8 to the x plus 2 power equaling 4 to the x minus 3 power. So I notice I can rewrite 8 and 4 as powers of 2. So I'm going to rewrite 8 as 2 to the third power raised to the x plus 2 power. Notice how I put the 2 to the third power in a parentheses. You want to do this when you rewrite a base in terms of another base and power. So that will equal 2 to the second power, which is 4 in a parentheses, raised to the x minus 3 power. Now, before we go on and set the exponents equal to each other, we need to raise powers to a power by multiplying. So I'm going to multiply the 3 by the x and the 2 by the x and the negative 3. Now we can set those powers equal to each other. So 3x plus 6 equals 2x minus 6, and then we'll just solve that simple equation and get x equals 12. Now remember, we can also write our answers in the form of a solution set. So write your set braces and put your solution in the middle. Sometimes you'll want to use a logarithm to solve an exponential equation. So if you can't rewrite the exponential in terms of the same base, then you can isolate the exponential expression and then switch to log form and then solve for the variable. So look at example 2 with me. 5 to the x equals 134. Well, I can't rewrite 134 as a base of 5. So that means I'm going to switch to log form. So you're going to build your logarithm. So we'll have log and then base 5, and that is 134 equaling our power, which is x. Now you can take your calculator and I'm just going to write this as change of base. So it will be the log of 134 divided by the log of 5. I'm changing it to base 10 equals x. And then let's round to hundredths place. So that will be approximately 3 4/100ths. Let's try another one. 10 to the x equals 8,000. We cannot rewrite 8,000 as a power of 10, so we can switch it to log form. Now remember that just the common log is base 10, and it's understood, so we do not have to write 10 as our base. And then on your calculator, you can just use your log key, which is automatically base 10, and do the log of 8,000, which is approximately 3.90. So that means 10 raised to that power will be pretty close to 8,000. Now let's talk about solving log equations. So we're going to do something similar that we just did with exponentials. We're going to use the property of equality, or it's called the one-to-one property. So in step 1, sometimes you will need to condense the logarithms before you solve. So then you'll have a single logarithm on both sides of the equation. So look at that example. If those logs are the same base, then you can use this property of equality, or one-to-one property, to rewrite it without the logarithms. So you're going to simply set the log values equal to each other. M equals n. Then you'll solve for the variable. One thing is that we need to remember that the log value will always need to be positive, so you need to check answers to your log equations to make sure when you plug them back into the original equation that your log values are positive. If they are negative, then that is not possible, and whatever you're checking is not a solution. So look at example 4 with me. We have the natural log of x minus 3 equals the ln of 7x minus 23 minus the ln of x plus 1. So the first thing I notice is that I can condense my logarithms on the right side of the equal sign, and I'll do that by division. Now I have one natural log equaling another. The bases are the same, so I can simply set those log values equal to each other. So x minus 3 equals 7x minus 23 over x plus 1. So I'm going to start by multiplying each side by the expression x plus 1 to get rid of that denominator. On the left side, when I FOIL, I'll get x squared minus 2x minus 3, and on the right side, 7x minus 23. Now I notice that I need to solve this quadratic, so I'll subtract my 7x over and add my 23. So let's try to factor. Two numbers that multiply to give me positive 20 and combine to give me negative 9. I believe that'll be negative 4 and negative 5. I can set those each equal to 0, and my two potential answers are positive 4 and 5. So I need to go back up to the original log equation and plug those in one at a time. So I get the natural log of 4 minus 3, which is 1, equals the natural log of 5 when I plug in 4 minus the natural log of 5. And then on the right side of the equation, when I condense, I get the natural log of 5 over 5, or 1, and that equals the left side, so that checks. Now let's plug in 5. So we get the ln of 2 equals the ln of 12 minus the ln of 6. On the right side, I condense by dividing. Natural log of 2 does equal itself, so both of these are solutions, and sometimes that happens. And see how you can write that in solution set form. Let's try this one. Notice on the right side of the equation that we need to condense. So let's multiply the 4 times the x plus 1. Now we have one log base 10 equaling another log base 10, so let's set those log values equal to each other, and I'm going to distribute my 4. Now I'm going to subtract my 3x's and subtract my 4. So I get x equals negative 7 potentially. So I start by plugging that into my first log expression, and I'm stopping because I can't have a log of negative 24. There's no power of 10 I can raise that to get negative 24. So we have no solution for this equation. Now sometimes you can use the definition of a logarithm to solve it, meaning you won't be able to use that one-to-one or property of equality, and you'll just need to switch forms. So you're going to switch to exponential form. Again, we're always going to check just to make sure that the solutions that we get will give us positive log values. So here I'm going to rewrite this in exponential form. So I know that that means 2 raised to the third power equals x minus 4. And then I draw that arrow to help you realize that's the motion of how you read a log. So 2 to the third power equals x minus 4. So 8 equals x minus 4. So x potentially equals 12. Let's check this. Log base 2 of 8 equals 3, and that's a true statement. So our solution is 12. So on this, we have a natural log. We can start by dividing by 4. So natural log of 3x equals 2. And then let's rewrite. This is a base e, so this will be e to the second power equals 3x. Now, if you do e to the second power on your calculator, you'll get a number decimal that doesn't end or repeat. So I'm simply going to write this as a fraction. So this is an exact form to express my answer as e squared over 3. Now let's try this one. So first let's condense on the left side. We'll multiply those log values. And now let's switch forms. This is a base 10, so 10 to the first power equals x squared minus 3x. Let's subtract the 10 over, and then see if we can factor. So two numbers that multiply to give us negative 10 and combine to give us negative 3, that would be negative 5 and positive 2. We set those each equal to 0 and solve, and our two potential answers are 5 and negative 2. So let's plug in 5, and that gives us a true statement. Log 10 does equal 1, and let's plug in negative 2. So right away we have a problem. We can't have a negative log value, so our only solution to example 8 is 5. All right, example 9. Again, let's condense. So we're going to take x times x plus 5, and then let's rewrite. So 6 to the second power equals x squared plus 5x. Subtract your 36 over. And then let's factor. So set your values each equal to 0 and solve. So our potential answers are negative 9 and positive 4. When we check negative 9 right away, we see it doesn't work because we get a negative log value. When we check positive 4, however, we get a true statement because we condense by multiplying, and so log base 6 of 36 does equal 2. So our solution is 4. All right, let's try another one. I hope you're getting good at this. So let's multiply those log values and then switch to exponential form. So 4 to the first power equals, and let's multiply x squared plus x minus 2. Subtract your 4 over, and then let's factor. So x plus 3 times x minus 2 equals 0. So our two potential answers are negative 3 and positive 2. When we check negative 3 right away, we stop because we can't have a negative log value. And when we check 2, we get a true statement. Because condensing, we divide. 4 divided by 1 is 4, and so log base 4 of 4 does equal 1. So our solution is 2. Now in example 11, solving an exponential equation. So we can't rewrite these as the same base, can't use the one-to-one or the property of equality, but we can rewrite as a logarithm. So our base is 3. So we start log base 3. Our power is 2x minus 1, and the value is 7 to the x plus 1. Now we can take that power of x plus 1 and pull it to the front. So this is a property we're expanding, property of logarithms. And so log base 3 of 7, put that on your calculator, and let's round to approximately 1.77. So our answer will be an approximation, an estimate. Now let's distribute that 1.77. And let's combine our x's on the right side and our numbers on the left side. So x will be approximately equal to, when we divide each side by 23/100, 12.11. Let's look at this application problem. How long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? So that means our n will equal 4. And when I mean by n, it's in our periodic interest formula. So let's put in what we know. Our ending amount is $3,600. Our principal is $1,000. Our rate will be 8/100. N is 4. And then what we're solving for is the exponent. So let's isolate it. Divide by 1,000. So 3.6 equals, do the math in the parentheses, 1.02 raised to the 4t. Now let's rewrite this as a logarithm. So log base 1 and 2/100, 3.6 equals 4t. To solve for t, you're just going to divide both sides by 4. And when you do that, so put the logarithm on your calculator, then divide the value by 4. So it will be approximately 16.2 years. All right, that concludes the notes. Chapter 3, Section 4, exponential and log functions.